Okay, so now for part 3 of homework 1 of computational methods, we want to go off and create a surface function which will plot the circle around our helical curve. Okay, such that that circle is always perpendicular. So we make our thick coil. Okay, so we go off and let's define this as surf. And what does it need? It's going to need time because our functions are parameterized. How do you say that word? Parameterized. Okay, parameterized, because our functions are parameterized. We also need a additional argument here, theta, so that Python can plot a circle for every unit of time, right? So what do we need? Well, we need our t and b frame. And to get our t and our n, we need to use our previous function here. Okay, so tangent and normal, we want to unpack it, is equal to Frenet curve t r mz. Right? Wrong. Because despite the fact that our curve is expecting 3 arguments, for the context of our problem, there is only one independent variable, time. Radius, big R, radius, and mz, linear rise in altitude, remains constant. So we have to use a lambda function here. Okay? So we say that lambda t is our dynamic independent variable. Okay? And r should equal, r remains constant. We have it defined up above. So does mz. Linear rise in altitude. Okay, so now we can go off and define our t and b curve. T equals tangent, n equals normal, and b equals, according to the Frenet-Serre formula, b, the binomial vector, is t cross n. So np or jnp dot cross t n. Okay, and we want to return the coordinates, the xyz coordinates of our each concentric circle, okay, along our helical curve. Okay, so to help visualize, we are essentially plotting a circle that's always perpendicular to this helical coil, so that it makes it thick. Okay, and we have to use the idea of perpendicular. We look at our b and our B and our T matrix, right? And that's the black vector and the red vector there. You notice that the plane that this produces is always perpendicular to the curve, right? We also have to use why don't I just code it out and I'll explain it along the way. Excuse me, I was going to sneeze, but it went away. So if we plot our circle right away, it's just going to stay at the origin, and it's going to just rotate while staying at the origin. So to get around that, we actually are taking our coordinates from our curve, so curve t, r, mz, and we displace ourselves from the origin towards that curve. So we use an addition operator. Then we go off and use the idea of a rotation matrix. And a rotation matrix states that if we take a rotation matrix multiplied by a vector function, matrix multiplied, well, the resulting vector function is that function rotated by whatever the rotation matrix is. In this case, the rotation matrix that we're going to use is the combination of our n and b vector, the red and black vector. Okay, and for matrix multiplication to work, the inners must match. So we have to stack our n and b column-wise. And the way we do that is jnp.stack. I believe it takes in that n and b, and believe it expects an axis argument, and we set that equal to 1. Okay. Matrix multiplied by, well, we now want our vector function, jnp.array. What is our vector function? Well, I've been saying it all along, it's a circle. We're plotting a circle to go around our helical coil, and it must always be perpendicular. So that perpendicularity is achieved by this matrix multiplication by a rotation matrix. So we should use little r, right? Little r is defined up here. That's the radius of our thick coil. Okay, little r multiplied by JNP dot cosine of theta times t. I think it's just theta, actually. I'm pretty sure it's just theta. And same thing, but with sine. GNP dot sine theta. Okay, so with that completed, we now have our function, which plots a perpendicular circle along our helical curve. In other words, our surface function.